So the rest of this section we're going to spend by talking about cyclohexane. Cyclohexane is by far the most important of the cycloalkanes. And the reason for that is it is, without a doubt, the most stable cyclic structure. And it's also a structure that we find quite frequently in nature. This being one of the most common and most important examples. This structure, as we can see, actually has 4 different rings in it. 3 of them are 6-membered rings, and the 4th one being the second most stable type of ring, a 5-membered ring. But this is the basic structure of a steroid. Anything that we would consider to be a steroid has this 4 different rings in it. And there's many other places that we find 6-membered rings showing up. Another example, or 2 more examples, are these 2 networks of cyclohexane rings. On the right we have graphite, and on the left we have the basic structure of a diamond. So why is it that cyclohexane is so much more stable than other cycloalkanes? So here's where you should pause for a moment and put together a model of cyclohexane. And when you do that, or now that you've done that, you should sort of twist your ring around in such a way that if you look down any of the carbon-carbon bonds, you should see all staggered conformations. So it will look something like this. And so this conformation, this orientation of cyclohexane, is what we regard or refer to as the chair conformation. And we represent it in 2 dimensions by the following drawing. So we have our 6 carbons of the ring. And if you look at your model, you should have 6 of your hydrogens, the ones that I'm drawing in green, that are pointing either straight up or straight down. And you'll notice that they alternate. As you will go around the ring, it's up, down, up, down, up, down. Then if you look at your model, you'll see that we have 6 additional substituents like this. Now we have names for each of these groups. The ones that I've put in green are known as axial, and the red ones are referred to as equatorial. And if you're trying to get your angles just right, you might notice that this bond, for example, is parallel to this line. This one is parallel here, and so on. And so the chair conformation for cyclohexane is so stable, again, because if we think of it in its Newman projection, all of the bonds are staggered, and we know that that's better. Now, back in the NMR chapter, at some point I probably asked you a question, if we had a cyclohexane that was unsubstituted, how many different types of hydrogens would it have? And hopefully we would still answer today correctly, 1. So are the axial and equatorial positions, are they equivalent to each other or are they different? Well, from the simple answer is they're actually chemically different. So this gray hydrogen, which is axial, and this purple hydrogen, which is equatorial, even though they're on the same carbon, they're actually not equivalent to each other. And so this is the first time we've seen an example of two hydrogens that are attached to the same carbon, but they're not equivalent to each other. But if they're not equivalent to each other, why is it that the gray and purple hydrogens come off as the same peak in NMR? Well, it turns out that unless we have certain substituents on our cyclohexane ring, cyclohexane can undergo what's called a chair flip. And you can actually do this with your model kit. But what you'll see happen is all of those green bonds, which are the axial ones, when we get a chair flip, they become equatorial. And all of the red ones, which were equatorial, will become axial. Like that. And again, if there's no substituents other than hydrogen, then this is just slightly under 11 kcals, 10.8 kcals per mole for this to happen. And typically anything under 15 or 20 kcals per mole can readily occur at room temperature. So what happens is that under normal conditions at room temperature, these two conformations just sort of flip back and forth with each other. And what ends up happening is that means that on an NMR timescale, the amount of time it takes to take an NMR spectrum, we can't tell the difference between them. But what becomes interesting and becomes important is when we start to get other substituents on here. And that's what we'll get to in a minute. But this chair conformation is not the only chair conformation for cyclohexane. There are actually a number of others, things such as the half chair and the twist boat. And then the other one that I'm going to show you in more detail, which is known as the boat conformation. So what I want you to do now with your cyclohexane model is kind of twist it a little bit. Remember, you don't have free rotation anymore, but you can move the bonds around a little bit. And I want you to move them around to the point where instead of all your bonds being staggered, they all become eclipsed. And so that's known as your boat conformation. We can also draw it like this. And we maybe start to see that it looks a little bit more like a boat if we do that. So the boat conformation is a lot less stable due to two major problems. One we've already seen, That's the fact that we have all these eclipsing interactions, but we also have an additional issue. So these two hydrogens sticking up from the boat, and yes, we're going to continue with the boat analogy. These are known as the flagpole hydrogens. What do you see about those hydrogens if you look carefully at your model? What you should start to see is that they get in each other's way. They're trying to occupy the same space. And two atoms trying to occupy the same space always works out badly. So a lot less stable than the chair conformation, and that's true for any of the other conformations of cyclohexane as well. So when we talk about cyclohexane, in almost every case what we want to be looking at is the chair conformation. And in the next video where I'll pick up is what happens to the chair conformation as we start putting substituents on there.